Hey everyone, in this video, I'm going to go over the ATC worksheet 1 for Chemotecine B. So in this video, I'm going to go over the content of the worksheet and then I'm going to walk through the practice problems. So first, we're going to go over the stability of alkenes, where we are going to rank the least stable to the most stable alkenes. We see in our least stable alkene, we have an unsubstituted alkene where the carbons of the double bond are not bonded to any R groups. Then we have our monosubstituted alkene where our alkene is only attached to one R group. Then we have our disubstituted alkene, where our alkenes are attached to two R groups, 1, 2, 1, 2, 1, 2. And we see that our cis and geminal alkenes are relatively similar in stability, and our trans alkene is more stable than both the cis and geminal alkene. And then we have our trisubstituted alkene, where we have three R groups attached to alkene, 1, 2, 3. Then we have a tetrasubstituted alkene, where we have four R groups attached to the alkene, 1, 2, 3, 4. So here are some special conditions where in the disubstituted alkene, the trans alkene is more stable than the cis alkene because there is less steric hindrance in the trans alkene. We see there is steric hindrance here where the R groups are closely to each other and have a more likely chance of touching each other, becoming less stable. Then we have an isolated alkene and a conjugated alkene. So if we see that an alkene can be delocalized or do resonance, then that alkene that is conjugated will be more stable than the isolated alkene, since the electrons are able to move around and be delocalized. And then we have a similar concept here, where we have a trisubstituted alkene and a conjugated disubstituted alkene, where the conjugated disubstituted alkene is more stable than the trisubstituted alkene because this conjugated disubstituted alkene is able to do resonance and delocalize its electrons in the resonance. Then we're going to go over the stability of carbocations, where we are going to rank the carbocations from the least stable to the most stable. We see in our least stable, we have a methyl, and then we have primary, where this carbocation only has one R group attached to it. And we have secondary, where we have two R groups, 1, 2. And then we have a secondary allylic, where this secondary carbocation here is able to do resonance. And then we have our tertiary carbocation, where we have three R groups around that carbocation, 1, 2, 3. And then we have our tertiary allylic carbocation, where we have this tertiary carbocation that is able to do resonance with the double bond. And so what I like to think about when I think about the stability of carbocations is that I think of the carbocations as having more friends than it is more stable. So we see here in the tertiary carbocation, it has three friends, 1, 2, 3, whereas in the primary carbocation, it only has one friend. So the carbocation that has more friends is the one that's more stable. This is also known as the hyperconjugation rule. Now let's go over the practice problems related to those concepts. So we want to rank the following alkenes from the most stable, 1, to the least stable, 4. So we know that the most stable alkene is the tetrasubstituted one, where we see this is tetrasubstituted. We have 1, 2, 3, 4. So since we know that this is tetrasubstituted, this is going to be our most stable alkene. Then we see that this alkene here is trisubstituted, since it has three R groups attached to that alkene. So this is our second most stable alkene, because this is a trisubstituted alkene. Then we see that these alkenes here are disubstituted because these alkenes have two R groups attached to it. So these alkenes are similar in stability, where I'm going to give them a rank of 3 because they are both disubstituted alkenes. And then we have this monosubstituted alkene where it only has one R group attached to it. So this is our least stable alkene because it is only monosubstituted. Then we're going to list the following primary carbocations in order of increasing stability. How do you explain the difference in stability? So we see here we have primary carbocations, and we want to rank them in from the least stable carbocation to the most stable carbocation. So we see here, this carbocation structure cannot do resonance. So since that cannot do resonance, that is the least stable carbocation. Then we see here, all the other primary carbocations can do resonance. Then we have to look at the next factor, which is the alkene. So we see here, this is the least stable alkene we have because this alkene here is mono-substituted, and this alkene here is di-substituted, but it is geminal. Whereas this alkene here is di-substituted and it is trans. So we see here that the mono-substituted is the next least stable, where it could do resonance here, there. Then we see that the next least stable is the di-substituted double bond that is geminal. And this can also do resonance here. Where is resonance structure? It's this. And then our most stable alkene is a di-substituted alkene with the primary carbocation that can also do resonance. And we see here in this resonance structure, this primary carbocation converted into a secondary carbocation. Then we're going to rank the following alkenes from the most stable 1 to the least stable alkene 7. So we see here, this double bond here is tetrasubstituted, making this the most stable double bond. Then we see in this alkene, this is a tri-substituted alkene, making this the second most stable. Then we see here, this is a di-substituted alkene, making this our third most stable alkene. Then we see here, we also have a di-substituted alkene, but this is a geminal alkene, 1, 2. And we see here, this is also a di-substituted alkene, but this is a cis. So we said earlier that the cis and geminal alkenes are similar in stability. So we're going to say that the geminal 4 is going to be similar in stability as the cis alkane 5. So 4 is similar in stability as 5. And then we have our mono-substituted double bond, which is our 6th most stable. And then finally, we have our unsubstituted double bond here. Since this double bond has no R groups, making this our least stable double bond. And for alcohol dehydration with the non-nuclear folic acid H2SO4, these temperatures that determine if the reaction is going to undergo an SN2, E2, SN1, or E1 reaction would depend on the professor. So given these temperatures here, these temperatures are for the series class. Okay, so let's go over the next concepts of the worksheet, which is alkene synthesis. So to synthesize or form alkenes, we could do an E2 reaction where we could either use a small strong base strong nucleophile like an alcohol or an alkoxide. And that would go for the Zaitsev product, where it grabs the hydrogen anti-periplanar to the leaving group, which it means that the hydrogen has to be on opposite side as the leaving group here. And since we use a small strong base strong nucleophile, we are able to form the more stable alkene since it is small enough to grab the preferred hydrogen. But if we use a bulky strong base strong nucleophile like LDA or tert butoxide, then we are going to grab the most available hydrogen that is anti-periplanar to the leaving group, which is this hydrogen, but form our less stable or less substituted alkene, because this bulky strong base strong nucleophile is not able to grab this preferred hydrogen since there is too much steric hindrance here. So if we use a strong base strong nucleophile like LDA, then we have to grab the most available hydrogen that is anti-periplanar to the leaving group, forming our Hoffman product or the less stable, less substituted alkene. So for the E2 mechanism, the strong base strong nucleophile attacks the hydrogen that is anti-periplanar or the opposite side to the leaving group. So in this case, we see that this hydrogen here is anti-periplanar to the leaving group, where if we use a small strong base strong nucleophile like hydroxide, then we're able to attack that hydrogen, form the double bond, and then kick off the leaving group. And this will give us this intermediate right here, where the ethyl group wedge is going to be on the same side as the hydrogen, and the methyl dash will be on the same side as the methyl dash. So since these carbons of the alkene are sp2, these groups are going to flatten out, where we see that the ethyl group is on the opposite side as the methyl group, or E to the methyl group. So we see that when we flatten out, this ethyl group has to be on the opposite side as the methyl group. And this hydrogen here is invisible, implied here. And for the next reaction, we have alcohol dehydration, where we use a non-nucleophilic acid like H2SO4, H3PO4, or HF to undergo this reaction. And if you're given heat, where the heat is equal to or above 140 degrees Celsius, then the E1 product will be favored. If you have Nisiri, or if you have a different professor, I would check their notes. So here's the mechanism for the alcohol dehydration. We start with a non-nucleophilic acid, where we have to look for our most basic atom, which in this case is alcohol, the oxygen of the alcohol, and that will get protonated. So after we protonate this alcohol, we turn this bad leaving group into a good leaving group, OH2+. Then this good leaving group would just leave by itself, forming our carbocation intermediate. And whenever we form our carbocation intermediate, we are going to look for any carbocation rearrangements like a hydride shift or methyl shift. In this case, we see that we could do a hydride shift to form the tertiary carbocation. Then we do an E1 reaction, where we could either grab this hydrogen, or this hydrogen to form the double bond. If we grabbed this hydrogen, we would form this double bond, which is a one, two, three tri-substituted double bond. If we grab this hydrogen, we would form this double bond, which is a geminal di-substituted double bond. But if we grabbed this hydrogen, then we are going to form the tetra-substituted double bond, which is the most stable double bond that we can get, which is why we're going to use the conjugate base that we formed in the first step. We form our acid catalyst by grabbing this hydrogen and forming our most stable tetra-substituted double bond here. Okay, so now let's go over the practice problems related to those concepts. So we see here we have NaOET, which is basically this ethoxide right here, 1, 2, which is a small strong base strong nucleophile. And this is going to signal that we have a E2 reaction here, but we have to have our hydrogen on the opposite side as our leaving group. So we see here our leaving group is this bromine, and our hydrogen here is going to be this hydrogen. So what we're going to do is we're going to redraw this structure in a way that is going to make the hydrogen on the anti-periplanar side to the leaving group. So when we do that, I'm going to move this dashed bromine to the planar phenyl group. When I do that, the phenyl group is going to become a wedge, and then the hydrogen is going to become a dashed. So once I rotated that, we have a dashed hydrogen here. Then we have a wedged phenyl group here. And then we have a planar bromine there. Now we're going to rotate this hydrogen to the planar side, moving this methyl group to the dash position, and then this phenyl group to the wedge position. So then we have this hydrogen on the planar position. Then we have this methyl group on the dash position, and then the phenyl group on the wedge position here. So now we see that this hydrogen is anti-paraplanar to this bromine group, where this ethoxide, a small strong base strong nucleophile, can attack that hydrogen, form the double bond there, and then kick off the leaving group bromine. Then what we're going to get is that we're going to get the dashes on the same side and the wedges on the same side. So we see here we have a dashed hydrogen, a wedged phenyl group, dashed methyl group, and then a wedged phenyl group. So since the carbons of the double bond are sp2, this is going to flatten out. So we're going to redraw this as this over here. Okay, so for the next problem, we see that we have the same ethoxide, small strong base strong nucleophile, which signals to me that this is going to be E2 mechanism. We also have a good leaving group here, bromine. So we have to look for a hydrogen that is anti-periplanar to the leaving group. We see that this hydrogen here is not 100% anti-periplanar to this leaving group because there are not 100% opposite sides to each other. Whereas this hydrogen here can be twisted or rotated enough to become anti-periplanar to the leaving group, which is why the ethoxide, small strong base strong nucleophile, will go ahead and attack that hydrogen B, form the double bond there, and then kick off the bromine leaving group, giving us this double bond here. So the reason why this hydrogen A is not able to twist or rotate enough to become anti-periplanar to this leaving group is because of this cyclopropane bulky group here, whereas the hydrogen B is able to twist and rotate enough to become 100% anti-periplanar to the leaving group bromine. Then we see here we have another ethoxide, small strong base strong nucleophile, which signals to me that this is an E2 mechanism reaction. So we have to look for the hydrogen that is anti-periplanar to the bromine. So we see here that this carbon here has the hydrogen that is wedged because this ethyl group is already dashed, but this hydrogen here cannot be attacked because this hydrogen is not on the opposite side as the bromine group. So we have to look at the next carbons. So we see here, this carbon here has two hydrogens, one wedged, one dashed, where we see this dashed hydrogen is anti-periplanar to that leaving group bromine, where this ethoxide can attack that hydrogen, form the double bond there, and kick off the good leaving group bromine, giving us this product here. And this dashed ethyl group remains unreacted, which is why it maintains its stereochemistry. Now we have a alcohol dehydration reaction mechanism where we converted this cyclopentane into a cyclohexene here. So let's draw out the mechanism of this. So we have acid, we start off with acid and heat. If you have heat that is greater than or equal to 140 degrees Celsius, the E1 product would be favored, depending on your professor. So we know that our E1 product here is going to be favored since we are adding heat. So the first step is to look for our most basic atom, which is oxygen in this case, and do an acid-base reaction with the acid, H3O+. Then we converted that bad H leaving group into a good OH2+ leaving group. So since we have a good leaving group now, we can make that leaving group leave, form our carbocarbon intermediate. And Now, since we formed our carbocarbon intermediate, we could do a weird step here where we form our cyclohexane ring, because we know that cyclohexanes are relatively more stable than cyclopentanes. So what we're going to do is that we're going to label our carbons to make this process easier. We're going to label this 1, 2, 3, 4, 5, 6, 7. So this bond between carbons 1 and carbon 5 is going to break, and carbon 5 is going to bond with carbon 6 to form our cyclohexane ring. So what we're going to have, so we're going to have this right here, where we have 1, 2, 3, 4, 5, 6. So we see that the bond between carbon 1 and carbon 5 broke, and we formed a new bond between carbon 5 and carbon 6. So then we have to draw what is attached to which carbon. We see at carbon 1, it's attached to one methyl group. At carbon 6, we see that it's attached to another methyl group. We see that carbon 1 used to have 4 bonds, 1, 2, 3, 4, but now it only has 3 bonds, 1, 2, 3, which gives it a carbocation there. Then our last step here is to form our double bond, or do the E1 reaction. We're going to use our conjugate base of water and reform our acid catalyst by grabbing that hydrogen and forming our most stable double bond that we can get, which is going to be our tetra-substituted double bond here, because we have 1, 2, 3, 4 R groups attached to that double bond.